Hello everybody, my name is Jacob Sanz-Robinson and the abstract I submitted to OHBM 2022 is called The Continuous Testing of Neuroimaging Results Across Pipelines and Datasets. So without further ado, let's get into this oral presentation. There is an increasing amount of neuroimaging studies that lead us to question the rates of result reproducibility in neuroimaging. Amongst other factors, such as pipelines and the hardware the experiment runs on, neuroimaging results are sensitive to variations in processing pipelines, which can contribute to scientific result reproducibility issues. Furthermore, researchers are often faced with multiple choices of pipelines that feature similar capabilities and which may yield different results when they are applied to the same data to find the same thing. As such, we find ourselves in a position where there is no clear ground truth, and it is unclear to researchers which pipeline they should use when all the pipelines yield different results. Continuous integration has been proposed as a method to evaluate and facilitate the reproducibility of computational experiments. So what is continuous integration? Well, it's a software engineering technique, and it consists of a series of tests that are launched as soon as new code has been committed to a code repository, and these automated tests check if the code is functioning as expected. However, continuous integration has not been applied in a neuroimaging context. In part, this is because it is very challenging due to the large storage and memory requirements of neuroimaging datasets and pipelines, and the privacy conditions of these datasets. In order to get around these limitations, we built a continuous integration system that can leverage distributed computation to run a given experiment across many different pipelines and datasets. Our goal in this abstract is to use that continuous integration framework we built to investigate the associations between hearing loss and brain structure. Now, this is an interesting use case for the platform because the robustness and the reliability of the result is unclear. This lack of clarity can be seen because some studies agree that hearing loss reliably predicts grey and white matter atrophy and is strongly associated with dementia. However, other studies found null results, whereby hearing loss had no effect on brain structure, and it's also possible that many other studies that had null results were simply never published. This is due to the file drawer effect, whereby studies that don't have significant findings are much less attractive to scientific publishers. In terms of a method, here is the software architecture we used for the continuous integration framework. There isn't enough time in 10 minutes to go into a lot of depth, but we can give a rough overview. On the left, you can see the data retrieval module. This module has the goal of downloading all of the distributed datasets onto the distributed storage that we may be using. In this case, we download the datasets from the Canadian Open Neuroscience Platform's repository using a piece of software called DataLad onto the Compute Canada distributed storage, and then we create a data provider for each dataset we download. On the right, you can see the pipeline containerization module, and this one has the goal of building portable containers for each of the pipelines. We do this by using a piece of software called Boutiques, which allows us to create descriptors for each of these pipelines. Given the pipeline containerization descriptors and the data retrieval's data providers, we can specify all of these datasets and pipelines and integrate them in the CBrain distributed computation platform. CBrain features an API. This API allows the piece of software we created to launch the heavy distributed computations we need on the Compute Canada distributed servers, all from within a continuous integration run. The workflow of a continuous integration run can be seen in the continuous integration module at the bottom of this slide. Inside the repository of the continuous integration framework, the user will find an experiment definition file where they can provide input in the form of the pipelines and datasets and parameters that they wish to use for their experiment. So when they commit and push this experiment definition file, it triggers a continuous integration run. And to trigger this run, we are using a continuous integration software called CircleCI. The framework's code, which is running on CircleCI, uses the CBrain API to communicate with CBrain and orchestrate all of the different computations across the different pipelines and datasets. It keeps track of these computations in a series of JSON cache files. At the end of the continuous integration run, we iterate through these JSON cache files and collect all of the newest results, generating an interactive visualization output and summary statistics of all the computations thus far. In terms of results, we created a functional prototype of the continuous integration framework, which we creatively called NeuroCI, and have made freely and transparently available at the following GitHub link. We use the framework to compute left hippocampal volumes with two different popular pipelines, FreeSurfer and FSL, on the PreventAD Alzheimer's dataset. The two graphs on this slide show the correlations between the left hippocampal volumes we calculated and a hearing loss measure called the worse ear's dichotic stimulus identification, or DSI for short. A higher DSI score indicates better central auditory system function. It's also worth mentioning that we removed outlying data points that contain volumes that were not in a biologically plausible range. As you can see from the graphs, the correlations that both pipelines yielded on the same data looks very different. The Pearson correlation between the results produced by the two pipelines was roughly 0.2 after outlier removal. We find that an XY plot such as the one on the right is very useful to see how a given data point varies across two different pipelines. It's also interesting to see the distribution of the results of the two pipelines as is shown on the left. Using these two graphs, we can see that FSL provides a larger spread in the values, as well as providing an asymmetrical distribution, which is skewed towards lower volumes. FreeSurfer, on the other hand, has a distribution that is roughly symmetrical and consists of consistently higher values than those outputted by FSL. These results are consistent with those in a 2021 study which is cited on this slide. So, to wrap up this presentation, one of the main points is that we built a continuous integration framework called NeuroCI, and NeuroCI leverages distributed computation to calculate results for a given experiment across multiple different pipelines and datasets. NeuroCI is generalizable to many different neuroscience experiments and is freely available for download on GitHub. As you saw from our use case, it allows users to systematically evaluate the result variability in their experiments and to pinpoint biases and discrepancies which could be caused by different tools and datasets, as well as quantifying their impact on the results. Ultimately, this allows neuroimaging researchers to consolidate knowledge in their field and explain uncertainty in experiments where there are reproducibility concerns. In health-related use cases, such as our example of hearing loss associations with brain structure, reliable results are very important because they can point us to the most likely robust biomarkers for researchers and practitioners. In terms of future work, the large discrepancy between the results obtained with FreeSurfer and FSL tell us that it is worth integrating additional pipelines into NeuroCI and additional datasets too, so we can evaluate the robustness and reliability of the result in a more conclusive fashion. I've just about run out of the allocated 10 minutes for this presentation, but I hope it was clear for all of you, and I hope you all found it as interesting as I found it was to work on. Thank you for listening.